Hi, this is our Developing Communications presentation on cosmology. The cosmological principle is a principle in astronomy where it's stated that the distribution of matter in the universe is homogeneous and isotropic except for local irregularities. This principle is used to simplify the equations and explanations of general relativity for models of the universe. The first assumption is homogeneity, where on the larger scales the local universe has the same physical properties throughout. Some of these properties include mass, density, expansion rate, and visible versus dark matter. The second assumption is isotropy, where on the larger scales the local universe looks the same in any direction that one observes. The third assumption is universality, meaning the laws of physics are the same everywhere in the universe. This principle is important as it allows a universe to change and evolve over time. The argument added to this principle is the perfect cosmological principle, stating that the universe does not change with time and there is no evolution.
Prior to the Big Bang, the density of the singularity meant that the temperature and pressure at this point was very high. This caused matter and antimatter pairs to be created, which, due to their opposite charges, annihilated each other. As the universe expanded following the Big Bang, it cooled, meaning that these pairs ceased to be created and mass annihilation took place. For reasons that we still don't fully understand, there was more matter than antimatter despite being created in pairs. This enabled basic atoms to form, which then bound to each other and created nuclei of basic elements such as hydrogen and helium. The Big Bang also created cosmic microwave background radiation, which we have discovered is not perfectly smooth due to variations in density and temperature. These variations enabled areas of space to be of different densities. In areas of higher density, the gravity is stronger, so nearby matter is pulled into these worlds and galaxies are created. However, we have noticed that galaxies actually consist of more mass than what we observe. This missing mass is what we call dark matter and is a term used to describe anything in the universe that we cannot see. Dark matter is not the only mystery surrounding the creation of our universe. Even now, the universe continues to expand at an accelerated rate, but we still don't fully understand why. The gravitational attraction between the matters should be slowing down expansion rather than accelerating it. Cosmologists refer to this constant mysterious force as dark energy. Despite the fact that dark energy makes up approximately 74% of the universe, we don't know much about it. This is because, unfortunately, dark energy is very weak, making it difficult to detect. All we really know is that dark energy continues to accelerate the expansion of our universe.
Now that you've learned about the Big Bang, dark energy, and dark matter, now let's talk about what happened to the universe from Big Bang to now. When looking at the timeline of the universe, the first thing we realize is that in the first few minutes of the universe, more has happened than has happened in the next few billion years. The first important thing that happened in the first billionth of a billionth of a billionth of a second after the Big Bang, when the strong nuclear force separated from the electromagnetic and weak nuclear force, triggering the great cosmic inflation. Here, pieces of the universe went from atomic nucleus size to solar system size. Only photons and energy existed at this point. Around a billionth of a second after the Big Bang, when the temperature was about 10 to the 15 Kelvin, the electroweak force separated into the weak nuclear force and electromagnetic force. This led to a formation of baryonic matter in near equal amounts of antimatter and matter, but after they annihilated each other, a slight excess of matter was left.
And this slight excess is what makes up everything that we see today.
At this point, the universe was still hot and dense. Thus, nuclei of different elements formed due to fusion, until the temperature cooled to about 10 to the 9 Kelvin, when fusion stopped, leaving 75% of baryonic matter as hydrogen, 25% as helium, and trace amounts of other elements, mostly lithium though. Matter was still ionized at this point, so any photons would be constantly absorbed and emitted by the free electrons and positive nuclei. Thus, the universe was featureless and opaque. Also, only 3 minutes have passed at this point. At the 500,000 year mark, the universe was a cool 3000 Kelvin, which allowed for neutral atoms to start existing, thus starting the era of atoms. Photons could also run free, so the first photons that ran free caused the CMB as we see today. Then, the atoms slowly started forming protogalactic clouds, which then coalesced into galaxies, starting the era of galaxies, which we currently live in.
What is the shape of the universe? The first thing to know is that the curvature and therefore shape of the universe is governed by the density. We can compare the density of our own universe to a figure called critical density. What is critical density? Critical density, P subscript c, is the value at which the universe's density would have to be for expansion of the universe to stop. We can work out critical density by using the equation P critical equals 3 times the Hubble's constant squared over 8 pi gravitational constant. As previously mentioned, when the critical density equals the density of our universe, at this point the universe will undergo no compression or expansion and is said to be flat. If the density of the universe, however, is greater than the critical density, the universe will have a spherical shape and will eventually collapse, described as a closed universe. If the density of the universe is less than the critical density, the universe will have a hyperbolic shape and it will remain in an expanding state, described as an open universe. Thank you for listening. I hope you enjoyed our presentation.